Hello and welcome to another online lecture for ECE 108. Hopefully our last one for the term. Hopefully nothing else comes up kind of in the future. So we'll start with a recap example. So pause the video for a little bit here and try solving this on your own, and then unpause it and we'll go through it together. Okay, so let's go through this one. So here we have L as a subset of R2 defined as this kind of set of these ordered pairs where X is less than Y, and we want to prove that this thing is a relation, give its domain, etc. So again, to prove it's a relation, we really don't have to do anything other than to notice, is this a subset of R2? Yes. So hey, it's a subset of R2, therefore a relation. Now, what's the domain? For the domain, we want to know what are all the numbers that I could plug in for X. So here, to figure out what the domain is, what we have to do is think like, hey, what type of X's would be related to various Y's? And here we can just notice, hey, X is always going to be less than X plus 1, right? So the ordered pair X comma X plus 1 is always in here, and I can plug in any number for X. So that tells me that the domain is the real numbers, and also that the range is the real numbers because, right, I can plug in any value for X, so X minus 1, that gives me arbitrary values. Okay, perfect. Now we need to compute what the range of this is. So again, the range is going to be the set of all of the Y's that are related to 1 or related to 4. So this guy or this guy. So we do our little number line trick again because it works for this case. Draw here, here's our 1, here's our 4. We need it to be need Y's to be bigger than 1, bigger than 4. So it's just going to be these. Okay, so there we go. And finally, for this guy, we just ask the opposite question. What are the X's? So here, we want the set of all the X's that are related to minus 1 or 2. So we get these two. Again, draw your little number line. Minus 1's here, 2's here, 2 wins out. So 2. Okay, perfect. Now what we're going to do is we're going to talk about other types of relations, and we're going to introduce a bunch of new definitions and kind of check out or figure out how to determine if something satisfies those definitions. Okay, and really the kind of bigger mathematical goal here is we now know that all of these symbols, right, things that look like this, less than or equal to, subset of, equals, greater than, like all of these operations are things that are relations, but they all kind of have different properties, right? So kind of what we want to do now is to explore what type of properties of relations would give us, say, this type of an operator, or maybe this type of a binary relation, right? So that's kind of the mathematical goal. From a CS perspective, relations appear in lots of various data type structures. Sometimes you can use them to compress data if you know certain structure of your data, that type of a thing. So knowing various types of relations and how to identify which ones are which, all that good stuff can be quite useful from a practical perspective. Okay, so let's jump in. So we'll first talk about reflexive and irreflexive relations. So a relation on the set X, so a subset of X squared, is going to be reflexive if for all X, X comma X is in R. Okay, so for every element of the set X, X is related to itself, is the way to kind of chase it out. So just kind of jumping ahead, you can think like, hey, for every real number X, X is equal to X, right? Therefore, this equals relation should be reflexive, right? Further, we have this other idea of irreflexive, and we say something's irreflexive if this isn't true. So if for all X in X, X comma X is not an element of R. Notice these aren't strictly speaking opposites of each other, right? For here, because we both have for all here, right? If we wanted to fully have irreflexivity be the negation of reflexivity, one of these would need to be a there exists. So they're not opposites, but they are in some sense kind of the opposite idea. Okay, so let's just look at some examples. So we can always talk about the null relation, right? and it always generally leads to weird things. So is the null relation on the null set? So when I say this, I'm saying treat the null relation as a subset of null set cross, maybe say null set, right? Under the standard definition is saying on here. So is this thing reflexive? Well, all we have to do is go back to our kind of basics of logic and ask, is this proposition true? Is it true that for every element of the empty set, that's related to itself within this relation? Yeah, there is nothing. So this one's trivially true, vacuously true. Same thing for irreflexive, right? This thing here is false, so yeah, that's going to be true. What about equals? Is it true that equals on R, that for every real number, x is equal to x? Well, yeah. Is it true that for every real number, x is not equal to x? No, so it's not irreflexive. What about this guy? Is it true here that for every real number, x is greater than x? Well, no, obviously that's not true, so this thing won't be reflexive, right? In particular, you could just pick a counterexample, right? 1 is not greater than 1, done, right? Now for irreflexivity, is it true that for every x, x is not bigger than itself? Well, they're the same thing, therefore it's the same size, so this one would be true. Therefore, it would be irreflexive, right? So hopefully just kind of practicing the definitions of how to do things in logic earlier make this section of the course a little bit easier, because it really just breaks down to do the logic, right? Okay, so what about this guy? Think about it for your own, maybe pause the video. Okay, so here, if we chase this out, is it true that x is less than or equal to x for all real numbers x? Well, yeah. And since it's true there, it's not going to be true here because there is something in the real numbers, right? Okay, and finally, if we look here, we've had the case true, 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 false, false, true, but we haven't had the case false, false. So let's build an example to break false, false. Okay, so to break false, false, what you have to have is one element, at least, needs to be related to itself, right? That would break irreflexivity. And you need to have one element, at least, that's not related to itself. That would break reflexivity. So that's what we did here, right? So I have the set A, B. A is related to A. Okay, well, it's not reflexive because B is not related to B. And it's not irreflexive because A is related to A. Right, so that's how you kind of get the counterexamples there. Now, when you think of the word reflexive, kind of the natural thing that might come to mind is like, hey, maybe I have a mirror and there's something here and I'm looking at the reflection coming back out type of thing, right? Or something along those lines, right? And it turns out that that kind of idea of reflection and reflexive, that kind of relation in those words, is actually a thing mathematically as well. So let's visualize what we mean by a reflexive relationship and an irreflexive relationship to get a kind of better mental idea of what's happening here. Now, again, this visualization is quite useful for like certain problems, but if you want to try to chase something out to prove something's reflexive, then you really do need to just break down and do the definitions. So here we go. So we can visualize reflections on finite sets. On infinite sets, obviously there's too many things to draw down. It'd have to be an infinite table, right? But what we can do is control this table of truth values to determine whether or not ordered pairs in the relation. So just to be concrete, here is the set A, and here is a relation on A. In particular, it's a reflexive relation on A because A1 is related to A1, and A2 is related to A2, and there's nothing else in A. So what we could do is we could write this as a table, right? So we write the values of one of the ordered pairs here, the values of the other ordered pair here, and we can put true or false to indicate whether or not the ordered pair that corresponds to this entry in the table is here, right? So I have A1, A1, that's in R, so I say true. Same thing for A2, A2. Down for these two bits, I put false because, well, it's not in the ordered pair, okay? Now this gives us a nice little way of visualizing things, right? So here we can say, for reflexivity, for instance, what type of things need to be satisfied. Okay, so let's chase this out. So for something to be reflexive, it needs to satisfy this property. For all x, x comma x is an R. Okay, so if x comma x needs to be an R, then I need this to be true, right? And I need this to be true. But these two terms over here could be any value I wanted, right? It could be true or false, and it still wouldn't break reflexivity, because reflexivity is just a statement about the diagonal, right? Just from the way that we built the table. So from here, that's what our table would look like. Here, these question marks could either be true or false. There's no restrictions on them. And yeah, right? So if I had a really, really big table here with lots of other things, I'd have true straight on the diagonals and question marks everywhere else, right? So that's what reflexivity tells me. So for instance, if I was dealing with the database and the database was, I knew that the relation modeled in the database was reflexive, I wouldn't need to store information on the diagonal. I could save all this information and just say, I know that's going to be 1, so I can get rid of a bunch of stuff there. It's not a lot of stuff, but it does make a slight difference there. Okay, so for your reflexivity, again, I need to satisfy this, and maybe just pause the video and try to think what this thing would look like. Should this be true? Should this be false? What should go where? Okay, so hopefully you paused the video and thought that through on your own. So let's think this through. So this is telling me that x can't be related to x. So on these diagonals, this needs to be false, and this needs to be false, but I can say anything I want about these again, right? So here I get false, false, question mark 1, question mark 2. Okay, so as we go forward with kind of other relations and all that kind of stuff, coming up with these diagrams can help you internalize things quite a bit. Okay, again, it's not a formal proof or anything. I mean, it can actually be a formal proof if you're legitimately working on a finite set, right? Because you can just do brute force, right? But generally, we're more interested in infinite set things, so that's where you have, yeah, some non-trivial work to do. Okay, so let's go back and notice something real quick. So here, we notice that there's kind of no really rhyme or reason of, like, are these both true? Is it true, false, false, true, or false, false? All of those possibilities are possible, right? But it turns out that we have a nice little theorem that tells us when we can have true and true. Okay, so it's a useful theorem that pops up for a few applications. Here we go. If R is a non-empty relation on a non-empty set X, then R cannot be both reflexive and irreflexive. Okay, so the key idea here is that R itself is a subset of something, right? So we have R is going to be a subset of X squared, right? So this is saying that R can't be the empty set, right? The empty relation, and X can't be the empty set. Given that that is true, then you can't be both reflexive and irreflexive. AKA, in my little table from earlier, the only way that I can write true and true is if both R is the empty set and X is the empty set, okay? Otherwise, like, you're going to have to break one or the other, right? It really just breaks down to there's something in the set, so you have to compare it to something, and that makes it so that you can't be both at the same time. Okay, so let's give a formal proof here. Okay, so like with everything with the empty set, kind of weirdness happens, but here we go. Let R be a non-empty relation on some non-empty set X and consider some X and X. Okay, so this is just setting it up, right? So since X is non-empty, right, we know there's something in X. Okay, so now I want to show that it can't be both reflexive and irreflexive. Now, the problem here is this word can't, right? Generally speaking, it's hard to show that you, if asked to show that you can't do something, that's really hard, right? You generally don't have too much to work with, right? For instance, show that there is no bijection. That means, like, show you can't build a bijection. How do you do that? Well, you assume you can and get a contradiction, right? That's the standard way to prove a negative, if you will. So because of that, we're going to do contradiction. So assume for the sake of contradiction that R is both reflexive and irreflexive. Okay, so what does this mean? Well, since R is reflexive, X comma X is an R. Done. Okay. Since R is irreflexive, x comma x is not an R. Okay? These are contradictory statements, right? Something can't be an element of R and not an element of R at the same time. Contradiction, therefore this case can't happen, right? And again, the fundamental problem is, like in the case where things are empty, if both of these are empty, then there is no x and x, and this argument breaks down, and it becomes, like, the statement becomes not true, right? You can be both of these. Okay, so kind of little fun fact there. So that's the end, for now at least, of talking about reflexive and irreflexive relations. These are generally considered the easy two because, like, there's fewer moving parts than what we're going to do, kind of going in the future. But this will come back as soon, like, once we come back from the midterm, we're going to start talking about different types of relations, and you're going to need to know these two, okay? So make sure you kind of digest them a little bit now. Okay, so now we're going to talk about symmetry, asymmetry, and anti-symmetry. So a relation R on a set X is said to be symmetric if, well, let's just think about that little diagram before we even come up with this, right? So if I give you a chart like this with stuff here, actually, I'll just be more vague. If I give you a picture like this and tell you that, say, the picture is symmetric, right? Generally what that means, say if I say symmetric across this line, that if I draw a little blob here, there'll be a little blob over here that looks the same, right? Geometrically, that's usually what you think when you say, hey, symmetric. Same thing here. So for all x, y, and x2, x is related to y if and only if y is related to x, okay? So if I have a little blob on one side, I have a little blob on the other side. Okay, so now asymmetric and anti-symmetric are different versions of breaking this symmetry, okay? So asymmetric breaks the symmetry by saying, hey, if I have a blob over here, I do not have the blob on the other side. So for instance, if this is filled in blob where these are all true, over here these won't be true. Okay, so let's introduce asymmetric. So it's asymmetric if, for all ordered pairs, if x is related to y, then y is not related to x, okay? So if I have one, then I have the other, right? And just students in the past have found this kind of weird. It doesn't matter what you call these symbols. You could say if y is related to x, then x is not related to y, just kind of by symmetry, right? You just need one direction to break the symmetry here. Okay, and finally we have anti-symmetric. This one's a little weird. It's basically, if you really, well, we'll get into that later, but it's a little bit weird, so let's just see the definition and go through it from there. So it's anti-symmetric if, for all ordered pairs, if x is related to y and y is related to x, then x is equal to x. Okay, so the reason why we really care about anti-symmetric is we still care about reflexivity and things like that, right? So if I look at, say, reflexivity and compare it to these guys, if I have something that is reflexive, right, and kind of over here I maintain symmetry, then I could still be symmetric, right? X is related to x, that poses no issues here. But if x is related to x, that poses an issue here, right? Because y is x, right? And this thing can't be, right? So asymmetry has an issue with compatibility with reflexivity. That's where this anti-symmetric comes in, right? It's kind of like being symmetric, but if I have these two things are both related to each other, then I'm on the diagonal, right? So it allows me to have this idea of reflexivity and this idea of being not symmetric in a meaningful way. That'll come back later when we start formally defining, say, greater than and greater than or equal to. Okay, so let's look at some examples. Null set on the null relation. Well, again, there's no x, right? So there's no ordered pairs. If there are no ordered pairs, all of these are true, trivially, right? No ordered pair, done. Okay. Equals on the real number. I need to determine, is this symmetric? Is this not? So the question I need to answer is it true that if A is equal to B, then B is equal to A? Is that true for the real numbers? Well, yeah, so it is symmetric. So since it's symmetric, anti-symmetry and non-empty, anti-symmetry also would follow, right, in this case. Because, hey, or sorry, not follow. Because, hey, like, this holds both ways, therefore I can't make that thing hold. Now, for anti-symmetry, you need to ask, like, hey, if x is equal to y and y is equal to x, does it follow that x is equal to y? Well, yeah, right? Pretty trivially true there. Okay. Greater than on the real numbers. So just play the same game, right? If x is greater than y, is that true if and only if y is greater than x? Well, no, right? Pretty clearly, like, that lots of things break, right? 2 is greater than 1, right? But 1 is not greater than 2, right? So that's a counterexample. So for asymmetry, is it true that if A is bigger than B, then B is not bigger than A? Yeah. So true, right? And then finally, for antisymmetry, would this be true? Well, let's just think this through. So I need to say, this is my premise, right? So what if if A is bigger than B and B is bigger than A? Okay. Does it then follow that A is equal to B? Okay. Well, for the real numbers, there are no numbers A and B that satisfy this, right? If A is bigger than B, then B is not bigger than A, right? So this is false, and this is question mark. I don't care what is true, if it's true or false, because the premise of the implication is false. This is vacuously true. Okay, so now less than or equal to here. Well, same idea. If A is less than or equal to B, does it follow that B is less than or equal to C? Well, sorry, I said C. Yeah, never mind. You get what I mean. This one's false, right? Because, yeah, it doesn't necessarily follow the other way. It can, right? For instance, you can have 1 is less than or equal to 1, and then that's true, and I can go 1 is greater than or equal to 1, right? So this thing fits, right? But it doesn't work for all of them, right? If I change this to 2, then that breaks. Okay. Oops. So now for asymmetry, you basically ask the same question. Is it true that if x is less than y, does it follow that y is not greater than or equal to x? Well, yeah, that one's false. Okay, and then finally for asymmetry, if x is less than or equal to y and y is less than or equal to x, does it follow that x is equal to y? Well, yes, so that one's true. Okay, so thus far we've seen kind of cases where we have quite a few of these little options here, but none of them have been anti-symmetric, right? So let's make things not anti-symmetric. Well, let's come up with some counterexamples to do some stuff. Okay, so here I have A, B, C, and I'm saying A is related to A is related to B, and B is related to A. Is this symmetric? So then you just really have to go through and check it out. Like if A, yeah. So A is related to A, therefore A is related to A. That one doesn't break symmetry. A is related to B, but B is related to A. That doesn't break symmetry, so it is symmetric. For asymmetric, is this true? Well, no, because I have these two pairs. Okay. And for anti-symmetry, is this true? Is there a case where x is related to y is related to x, but x is different than y? Well, yeah, right here. This breaks it. So this one's false, right? Because A is related to B is related to A, but A is not B, right? That's the issue there. Okay, so here's another one. So A is related to B is related to A, and now A is related to C. Symmetric? Well, A is related to C, but C is not related to A, so not symmetric. Antisymmetric? Well, A is related to B and B is related to A, so not antisymmetric. Asymmetric. And antisymmetric, well, it's also not going to be antisymmetric, right? And the reason why here is A is related to B is related to A, but A is different than B. Okay. So those are just a handful of examples there. You can spend a bit of time and try to digest these and convince yourself why these various things are true, but it really just breaks down to, I have a proposition from propositional logic, actually first order logic, and I just need to determine, is this true, is this false? So it's really just a logic game once you kind of internalize it. And again, you need to memorize these definitions to be familiar with them. You'll have a homework set after the midterm, of course, and that'll help you get used to these guys. But yeah, okay. So now we can also visualize these concepts just like we visualized things from before, right? So let A be this set, let question mark be true or false, and I is just going to kind of indicate a different question mark, and P, Q, and R be propositions. So if something's symmetric, it has to satisfy this, right? So now I need to ask, what do these things look like? Well, if I kind of draw this out, sitting here, I'll have the diagonal, okay? On the diagonal, let's just think what could happen. Well, if one of these diagonal bits is true, right, then that doesn't break this, right? Also, if it's false, it doesn't break this. This thing would still be true, right? So in that case, we can put true or false on the diagonal. It doesn't break anything, right? So these are going to be little wild cards on the diagonal, right? Question marks. Now, for the off diagonals, they could also be true or false. There's no restriction, right? I could have nothing is related to anything, and it's still going to be symmetric, right? But if I do something over here, I have to do the same thing over here, right? So because of that, this is the table we're going to get, right? So on the diagonal, it could be true or false. Don't know what it's going to be, right? But on the off diagonals, I have to maintain symmetry. So if this is the proposition P, say if it's true, then this has to be true. If this is false, this has to be false, right? That type of thing. And now here you can see for symmetric databases, you can store a lot of information by kind of removing stuff, right? Well, you can condense information, right? I don't need to know this stuff, right? If I know this stuff over here in the diagonal, I know everything below the diagonal, right? So that's kind of a useful little fun fact there. Okay, so an asymmetric relation has to satisfy this property, right? If x is related to y, then y is not related to x. So let's kind of chase this out. So if I think about the diagonal now, could the diagonals be true? Well, on the diagonal I have x and x, so this would be x and x, right? And this would be x here. Well, if x is related to x, then x can't be related to x. That's a problem, right? So I'm going to have to be false on the diagonal, otherwise this whole thing breaks, right? Now, for everything else, I just need to negate things, right? It has to have the opposite sign. So here's what we get. It's false on the diagonal, right? So I kind of lose the idea of reflexivity, right? Reflexivities are, kind of dead in the water for these asymmetric relations. And I kind of get these ordered pairs pairing up like this. Okay. So finally, we can talk about asymmetric relations. Antisymmetric relations. And it turns out antisymmetric relations are quite a bit more complicated. So we need for a relation to be antisymmetric, we need it to satisfy this, right? So let's kind of break this down to think about what would happen if it was true. Well, if the hypothesis is false, then the statement is trivially true, right? So now in this case, let's consider what could happen. Well, one, we could either have that this is an R and this thing's not an R, right? Or swap the X's and Y's. Or the other option is that both of these aren't in R, okay? So this gives us two kind of cases here where this would be true, right? So one is true and the other one's false, or they're both false, right? Both of those are possible options. Okay, and if the hypothesis is true, if they're both related to each other, then X has to equal Y. Okay, so if we think this through in terms of diagonal, off diagonal, right? So on the diagonal, we could have true or false, right? And it doesn't break anything. So we'll have our question marks on the diagonals, right? Because if they're both true, like if X is related to X and X is related to X, then this thing trivially holds, right? And if X is not related to X, then the implication still holds, right? So I don't break asymmetry by having true or false here. But for the off diagonal, I'm allowed to say make this thing P, right? So P could say be true or it could be false, right? And now I need to think like what has to happen if P is true? What happens if P is false? Well, if P is true, say if X is related to Y, then I need this implication to hold, right? So for the implication to hold, it then has to follow that the other guy over here would be, say, false, right? Because, in particular, if this was true, I would have X is related to Y and Y is related to X. Then X would have to be equal to Y, but I'm not on diagonal, right? So if P is true, this has to be false. Now, if P is false, this other guy could be true or false because of these cases here, right? So here we get kind of a complicated thing where I put primes, right? So question marks on the diagonal could be true or false, doesn't break anything. If P is true, then this thing has to be false. If P is false, this could be true or false. So we need a way to encapsulate that information, and the way we do it is with this prime term, and we say, hey, X prime is false if X is true, and it's either false or true if X is false, right? So that's kind of the messiness that is anti-symmetry, but it's required to play nice with reflexivity. Okay, so now we have quite a few things that we've introduced. Since it's a lecture video and it'll be shorter than a regular lecture, if you find you're confused about some of these terms, go back and think about them a little bit. But now what we're going to do is we're going to combine these things together and say, what type of relationships can we put between these types of relations? Okay, so we'll have two theorems with proofs. So first one, if R is an asymmetric relation, then R is anti-symmetric. So if you go back and look at the little table, you'll find that this was true for everything in the table, but yeah, the question is, why is this true? Okay, so we'll give a formal proof for this, and to do so, we have to be careful with the null relation. Generally speaking, hopefully you've learned that the null set causes all kinds of issues with edge cases, right? So because of that, you need to be careful with handling it. So handle it first. So let R be an asymmetric relation. Okay, my goal is now to show that it's anti-symmetric. Okay, I know nothing about R, I know nothing about the set A, right? So I can't really use anything other than the definition of asymmetric and anti-symmetric. So we know the null relation is asymmetric, and we know the null relation is also anti-symmetric. So if it's the null relation, then I'm done, right? And you do need to cover this because the argument that we're going to use will not work for the null relation, right? So if you just wrote this argument without this line, the proof would not work. Okay, so now if R is not the null relation, then I know something about it, right? I know if R is not the null relation, then A has to have something in it, right? A in particular has to have a thing called X, right? So now I can talk about this ordered pair, right? So I can say, hey, since R is antisymmetric, whenever X is related to Y, it follows that Y is not related to X. And again, here, well, not really again, but here I'm mixing terminologies to get you used to this stuff, right? These mean the same thing. Well, this means X is related to Y, this means Y is not related to X, but they're two different syntaxes, two different ways of expressing the same types of ideas. Nevertheless, okay, so if I know these two things are true, from here, it follows that this thing is always false, right? If X is related to Y and Y is related to X, well, that's never true, because if X is related to Y, then Y is not related to X, right? So if this one's true, this one's false, right? And there's no, like, if this one's also false, yeah, it's still false, right? So because of that, and the fact that in our definition of asymmetry we have, if this is true, then X is equal to Y, it follows that that implication is always true. And therefore, it's going to be vacuously anti-symmetric. Starting to lose my voice again. If R is a non-empty asymmetric relation on A, then R is not symmetric. Okay, so the key idea here is non-empty again. If it's empty, then it's both, right? But this just says that asymmetry and symmetry are kind of opposite things. Like, you can't have both unless you're empty. Okay. So let R be a non-empty asymmetric relation on A. Now, we need to unpack what we know about R being asymmetric. Since R is asymmetric, whenever X is related to Y, we have y is not related to x, right? Okay, so by the definition, r now can't be symmetric because for all x, y, and a squared, this thing implies that this is not true, therefore this can't imply that this is in fact true. And the key idea here is this is non-empty, right? So there actually is something here, right? If there was nothing there, then it would be trivially true via the funness that is vacuous truth, right? So that's where this guy breaks down. Okay, so again, these are like mostly kind of playing with definitions, chasing things out. Try to sit down and like I could ask you either, not on the midterm obviously, but for the final I could ask you either of these type questions or similar questions where you'd have to kind of know the definitions and break things down, right? So just get a little bit of practice with that type of stuff. Okay, so now I'm going to write a claim without proof. Suppose R is a subset of this, then R is asymmetric if and only if it is antisymmetric and irreflexive. Now, I suggest taking this as a practice problem, right? Now, notice you have to do two things. One, you have to prove this direction, and you also have to prove this direction, right? So I'd recommend sitting down and trying to prove this. What does it mean for it to be asymmetric? Write out that definition. What does it mean to be antisymmetric? What does it mean to be irreflexive, right? In the forward direction, you need to go from asymmetry to antisymmetry, which kind of a hint. Yeah, maybe something similar to one of these. Not exactly, but similar. Then you also need to go from asymmetry to irreflexivity. Then on the other bit, you need to use these two definitions together to get to asymmetry. Okay, so see proof. I highly recommend actually reading the proof and all that good stuff. Okay, so for assigned reading, read these pages. In Schwalm's, I'll put this in the slides, it's not there currently, but you should read the types of relation sections. In particular, read the stuff here on reflexivity. There's lots of examples, lots of chasing things out. Read here for symmetric and antisymmetric, and then this will be the next lecture, right? So very little reading to do there for now, but yeah, definitely digest a little bit of that, okay? And for your meme, we have this guy. Math is math. Math is reflexive. Ha ha ha. Okay, so that'll be it for this lecture. We do have tutorials again coming up on Friday. They are more of a review session for the midterm, so I highly suggest you go to tutorials, even more so than usual. Okay, so have a good day, everyone, and talk to you guys in a couple weeks.